So before anything else, let me introduce to the topical workbook for computer science 2210 or 0478. This is the workbook 1 for paper 1, basically computer systems. And as you can see from the table of contents, I've included questions on each and every subtopic from the syllabus along with the mark scheme. And these are some of the actual questions, actual pages as a preview from the workbook. Section 1.1, 1.3, 2.2, 3.2, 5.3 cybersecurity and artificial intelligence. This is just to show you a glimpse of what type of questions are included in the workbook. There are many more questions where these come from, and around 18 to 20 questions on an average are included for each and every topic. A must buy if you want to boost your grade. Similar to the paper 1 workbook, I have designed a paper workbook for paper 2 as well. This is for algorithm, programming and logic for CIEs either 2210 or 0478 GCE or IGCSE Computer Science. As you can see, it contains questions on every subsection of the syllabus content for paper 2 along with the mark scheme, so you can understand each and every question, each and every algorithm. These are some of the few pages from the workbook just to give you a glimpse of what type of questions are included. As you can see, this is 7.1, this is 7.7, 8.3 and section 10 Boolean logic. So a lot more questions are included in the workbook. A must buy if you want to have a very good score in your Cambridge examination. Order now. Assalamu alaikum warahmatullahi wabarakatuh. Welcome to another physics lecture. Today we are going to continue our topic from our last lecture, that was 5.2 radioactivity. In our last lecture we discussed what is radioactivity and what are the different types of emission of radioactive particles and rays, as well as we discussed some of the properties or the characteristics of different types of emission. We studied about alpha rays, about beta rays, about gamma rays or alpha particles, beta particles and gamma radiation, and then we discussed some of their properties, penetrating power and ionization power, and then we discussed some of the uses of these three types of radiation as well. Now we are going to talk about another property or another characteristics, deflection of radioactive particles in an electric field. If these type particles are present in an electric field, the alpha particles, which consist of the protons, 2 protons and 2 neutrons, it has a positive charge, so it behaves like a positively charged particle, and they are deflected towards the negative plate or the negative terminal, whereas the beta particles are the fast moving electrons carrying negative charge, so they are deflected towards the positive plate or the positive electrode. Beta particles are always more deflected, or they are much strongly deflected due to having very less mass as compared to alpha particles, while the gamma radiation just keeps on traveling in a straight path, as gamma radiation does not have any charge at all. Here's an image to make you understand it much better. As you can see over here inside the light block, we have the radioactive source which is emitting all three types of radiation. And as you can see, alpha particles are slightly deflected towards the negative plate. Gamma rays just keep on traveling in a straight line, whereas beta rays are deflected towards the positive plate by a greater angle, by a greater force, as they have very less mass as compared to alpha particles. Hence they are attracted more strongly. Deflection of radio particles in a magnetic field. If you have to find the deflection of radioactive particles while in a magnetic field, then alpha particles and beta particles, both of them are deflected, and by using Fleming's left hand rule, the one which you studied In section number 4, electromagnetism, you can still apply that rule in order to find out what would be the direction of the deflection of alpha particles and beta particles. Basically, we use the Fleming's left-hand rule to find the deflection or the direction of deflection for alpha particles, and by using the Fleming's left-hand rule, we get to know that alpha particles still, even in the magnetic field, they also behave like positively charged particles, whereas beta particles, they are also deflected. However, their direction of deflection is always opposite to the alpha particles, as they have a negative charge, whereas gamma radiations are not deflected at all, as they are uncharged. Therefore, they are unaffected when passing through a magnetic field. They just keep on traveling in a straight line. Now, how would you apply that Fleming's left-hand rule which you studied previously in the scenario of radioactivity and magnetic field? Well, the rules are simple. FBI, your thumb points towards the force acting, your index finger points towards the magnetic field or the direction of the magnetic field, and your second finger would point towards the over here. Instead of current, it would point toward the direction of travel of alpha particle or your radiation. This is the only difference between the Fleming's left-hand rule that you previously studied and the one you need to apply in radioactivity. That for the second finger, you are going to consider the direction of the direction of travel for the alpha or beta particle, not the direction for the current. Okay. Now, if I check where the alpha particle would be going towards, so I'll be aligning my index finger towards myself, as a dot means the field is coming out of the page, and my second finger should be pointing towards the right hand side, as alpha particle and is going towards the right hand side from left hand side. As you can see, the source is on the left side and the particle is going towards the right, and that means that my thumb is pointing downwards. That means the force would be acting downwards on the particle, hence the alpha particle would be deflected downwards. And as we discussed above, for finding direction of beta particle deflection, we first find the direction of alpha particles, and at 180 degrees from there, or at the exact opposite of that, we would find the deflection of beta particles. So beta particle would be deflected upwards, whereas the gamma rays would keep on traveling in a straight line. I hope you have understood this well enough. Otherwise, you can simply mention your queries below in the comments. I'll be sure to reply them. Next, we have something that is known as nuclear fission and fusion. Now, these are two special reactions which radioactive nuclei undergo. So firstly let's discuss nuclear fission. Nuclear fission is a reaction when the nucleus of an atom is splits into a lighter nuclei through a nuclear reaction which is termed as nuclear fission. Fission basically means a breaking of an atom or splitting of an atom into two different other lighter elements. This decay can be natural and a spontaneous splitting by radioactive decay, or can actually be simulated or stimulated in a lab by achieving necessary conditions, like if you bombard a nucleus of a radioactive element with neutrinos, you would start a nuclear fission reaction. The resulting fragments tend to have a combined mass which is less than the original. The missing mass is what is converted into nuclear energy. This is a diagram of a nuclear fission reaction. an incident neutrino hits a fissionable nucleus, making it unstable and critical. Hence, it splits into two daughter nuclei, creating a lot of energy and producing fission products, as well as more incident neutrinos or neutrons, which then hit other elements available in the other atoms of elements of same element available in the vicinity, available in the surrounding, causing a chain fission reaction. Once this reaction is started, it would not end before all of the available elements have been splitted. This is the reaction that goes inside a nuclear or an atomic bomb, or which is done inside nuclear power plants to create energy. Nuclear fission. It is a reaction through which two or more lighter element nuclei collide together to form a heavier nucleus. The nuclear fission process occurs in elements that have a very low atomic number, such as hydrogen, and two hydrogen can combine together to become a helium nuclei, which again creates a lot of energy, and this is what is being continuously going on in sun and other stars. And as a result, as you know very well, these stars are able to create a massive amount of energy in form of heat and radiation. Nuclear fission is the opposite of nuclear fission, in which heavy elements diffuse and form lighter elements, whereas in fusion, the lighter elements combine together to form heavier elements. Both nuclear fission and fusion produce a massive amount of energy. Nuclear fusion is what goes on in sun and stars to produce massive energy in form of heat, light, and radiation. This is a diagram of fusion reaction. A deuterium atom as well as a tritium atom can come together and be combined to form a helium nuclei plus a neutron that would go ahead and cause other chain fusion reactions, just like we saw above in case of chain nuclear reactions. And a lot of fusion energy is released in form of gamma radiation, in form of heat, in form of light, etc. Fission in nuclear power plants. One of the major applications of a fission reaction is the production of electricity by nuclear power plants. Nuclear fission is an advantageous method for producing power for several reasons. They are used to generate electricity, making use of the nuclear fission reaction. The heat from the nuclear reaction or the nuclear fission is passed on to a working fluid, which in turn runs through steam turbines. These either drive a ship's propellers or turn electrical generator shafts, creating electricity. Next is the concept of half-life. The number of radioactive atoms in a substance decrease exponentially over time. Therefore, every radioactive element has a characteristics time called the half-life. After that time, the number of radioactive nuclei in the sample would have decreased to exactly half the number originally present. The half-life of a sample of a radioactive isotope is defined as the time taken for half the original unstable radioactive nuclei to decay. Different radioactive elements decay at different rates, and hence they all have their own very specific different half-life. The radioactive decay of sodium-24 can be studied using a GM tube or a Geiger-Moller tube and a counter to find the number of counts per second at various time intervals. The half-life of sodium-24 is 15 hours. Initially, there are 20 million undecayed sodium-24 nuclei. After 15 hours, one half-life time, there will only be 10 million nuclei left. The half-life of a radioactive element gives an indication of its stability. Radioactive elements with longer half-life are more stable. And how would you count a half-life using a GM tube and counter. Once one half-life has passed, the number of counts that element is producing would also be halved. As you can see, after every half-life, the size of sample decreases in weight, and the number of half-lives increases, the count produced by that certain element would also be decreased by half or by 50%, as well as the mass of that sample would also decrease. Lastly, we have the uses of radiation. The first use is tracers. A radioactive tracer is used to follow the path of a compound through a system. It can be a medicated capsule where the doctors are trying to find or trying to look inside a patient's body, or it can be used to find leaks in underground pipes that carry water or oil. They can be detected by injecting small traces of radioactive compounds into the flow. GM tubes on the surface can then be used to detect the leakage. Medical and biological uses. Immature cells and cells that are growing or dividing most rapidly are most sensitive to radiation. This is made This is used of in radiation. This is made use of when we are treating cancers by the use of radiation. Often cancer cells are growing rapidly and are therefore much more likely to be killed by a high dose of gamma radiation than a normal cell that divides less frequently. So the more rapidly dividing cells have a higher chance of being killed by gamma radiation. Then we have the archaeological dating. The atmosphere contains a small portion of radioactive carbon-14 which is absorbed by living cells, plants and trees, etc. as a result of photosynthesis. The half-life of a carbon-14 sample is about 5,568 years. So there is a negligible disintegration over the lifetime of most plants. However, once the plant has died, no further carbon-14 is taken from the environment. Hence, the decay starts. The proportion of carbon-14 inside the plant starts to decrease. After one half-life of 5,568 years or 5,568 years, the proportion of carbon-14 remaining is down to 50% of its initial value. Measuring the activity enables the age, time since death of the dead sample to be calculated by comparing it with the activity of same mass of living wood or living flesh. Then using the value of half-life of carbon-14, the age can accurately be determined. Another use of this process is also known as carbon dating. Another use of radioactive elements is inside smoke detectors. Alpha particles are used in smoke detectors. The alpha radiation will normally ionize the air within the detector, creating a current. The alpha emitter is blocked when smoke enters the detector. The alarm is triggered by a microchip when the sensor no longer detects alpha particles. Measuring the thickness of material. The thickness of material can be used can be measured by the use of beta particles to gauge the thickness of different types of material and metal sheets. As a material moves above a beta source, the particles that are able to penetrate it can be monitored using a detector. If the material gets thicker, more particles will be absorbed, meaning less number of particles will get through, and the count on the counter of detector would decrease. hence an alarm would be sounded, or if the material or the sheet gets too thick, the opposite will happen. In both situations an alarm will be sounded. So or the machine would be the machine, if it's an automated machine, it would be able to detect it and adjust the thickness accordingly. Beta radiation is used here because it will be partially absorbed by the material, 1 millimeter, 2 millimeter or 3 millimeter. If you are trying to make such thin sheets of metal, beta particles are ideal as they would only be partially absorbed. If you would be using alpha particles, there's a chance they would completely be absorbed and hence the detector will not work, whereas no matter the thickness of your material, the gamma radiation would most likely always penetrate through, hence it would not work as well. Sterilizing food and medical equipment. Gamma radiation is widely used to sterilize medical equipment. It is most suited as it has the most penetrating power to irradiate all sides of the instrument. Instruments can be sterilized without removing the packaging. Food can be irradiated in order to kill any microorganisms or germs that are present on it. This makes the food last longer and reduces the risk of foodborne infection. Okay, let's move on and see what do we have. Safety precautions while handling radiation. Ionizing radiation can damage human cells and tissues at high doses. This can be in terms of cell death, tissue damage, mutations, or they can even cause cancer. As a result, its use needs to be kept to a minimum. However, the benefits of using radiation in medicine can outweigh the potential risks. The risks posed by radiation are smaller than the risk associated with leaving the condition untreated. Tissue damage. Radiation is effectively used to destroy cancerous tumor cells. However, it can cause damage to healthy tissues if it is not properly targeted. This is mostly from high energy radiation such as gamma rays and X-rays. If the atoms that make up a DNA strand are ionized, then the DNA strand can be damaged. If the DNA is damaged, then the cell may die or DNA may be mutated when it reforms. This mutated cell can replicate itself and cause a tumor or can start cancer in your bodies. The word mutation in physics is not as fun as when it is used in comics, where if you have a mutation you get superpowers. In real life you just get a very nasty rash and probably a cancer or a tumor or blisters on your skin, which are not fun at all. Acute radiation exposure can have other serious symptoms as well. It can cause skin burns, blisters, and radiation can also reduce the amount of white blood cells in the body, making a person more susceptible to infections by lowering their immune system. And because of this, it is very important to handle radioactive sources very carefully. Safe storage of radioactive material. The risk associated with handling radioactive sources can be minimized by following a few simple procedures. Store the source in lead-lined boxes and keep at a distance from people. Minimize the amount of time you handle sources for and return them to their boxes as soon as you have finished. During use, keep yourself and other people as far away from the sources as possible. When handling the sources, do so at arm's length using a pair of tongs, and also you can wear aprons which are lined with lead. When using tongs, gloves and safety specs are usually unnecessary when handling radioactive material unless there is a risk of the material leaking onto other things. Disposing of radioactive waste. If an isotope has a long half-life, then a sample of it will decay slowly and will remain radioactive for a long period of time. Sources with long half-life values present a risk of contamination for a very long time. Hence, such sources should be buried underground in proper lead encapsulated canisters to prevent them from being released into the environment. Example questions. The diagram shows a nuclear reaction which the shaded particles are uncharged, that means they are neutrons. What are the products shown in this reaction? A helium atom and a neutron, a helium atom and a proton, a helium nucleus and a neutron, a helium nucleus and a proton. The correct answer, first of all, you would notice that this is the diagram of a fission reaction, and in a fission reaction we always have a neutron produced as well as a helium nucleus or some other nucleus. So this in fission products there will be alpha particles or human nucleus and a beta particle, fast moving electrons or neutrons will be produced. So this is the this is most like this is not a fission reaction. Don't go for this. This is a fusion reaction. This is a deuterium and this is a hydrogen. They are forming together in order to produce a helium nuclei and a neutron. This is a fusion reaction, but C would be the correct answer. A narrow beam of radiation from a radioactive source travels out of the page through point X. The poles of a magnet are placed on either side of the beam. Radiation is now detected both at X and Z. Which type of radiation are present in the beam? Alpha and beta, alpha and gamma, alpha, beta and gamma radiation. Now, in order to, first of all, we'll check for alpha radiation. If point X has stayed without any changes, that means the presence of gamma radiation, as they are not deflected by any electric or magnetic field. A new detection at Z means either alpha or beta. So we are just going to use Fleming's left hand rule. Our magnetic field is always from north to south. So we will be aligning our index finger towards the right hand side, and the direction of the alpha particle, the direction of the radiation would be towards ourselves as it is coming out of the page. And at that position, if it was alpha particles, Z would have appeared above X. But Z is downwards, that means it must be beta particles. So D should be the correct answer, beta and gamma radiation. And you can simply pause the video and read this explanation as well. This is just what I've explained. There is a radiation detector in a laboratory where there are no radioactive samples. The detector is switched on and shows an average count rate of 22 counts per minute. State why the radiation detector shows this. Because this is the background count or the background radiation. A sample of isotope X is placed 2 cm from the detector and the reading is 8000 counts per minute. The sample is moved at a distance of 10 cm and the reading decreases to an average of 22 counts per minute. Explain why the reading returns to the original value. Alpha particles are absorbed by the air and they cannot travel for more than a few centimeters. If your detector is 10 centimeters away from the radiation source, that means all the alpha particles would be absorbed by the air. Hence, no alpha particles would reach the detector. It would only detect the background radiation. A sample of yttrium-90 is placed close to a radiation detector. There are no other radioactive samples in the laboratory. A counter records the count rate, and this is a graph for that. Using figure 10, determine the average background count rate. Average background count rate would be somewhere over here where the line becomes flat, so it is around 18 counts per second. Yep, per minute, sorry, per minute. this is count rate is in per minute. Suggest two different origins for the background count. It can be rocks, the building material, the coal, the radon in air, space, sun, cosmic rays, weapons testing, nuclear waste. There can be many background sources for background radiation. Using figure 10, determine the half-life of deuterium-90. Show how the answer is obtained. First, calculate the corrected count rate by removing background count. So as you can see, our current count rate is somewhere around 74. Minus 18 from there to get the corrected count rate, that would be 56. Now use the graph to find the time it takes for it to become half, that is 24. That is 28, sorry. So the time it takes to become 28 would be somewhere around here. We'll just mark 28 over here and then draw a line and go down and see how many what time it takes. Add 18 to it to get the corrected reading from the graph. The 18 we minused before, we have to add it now. So it becomes 46. 28 was the supposed half-life. As our graph is not corrected, it is having background radiation, so we'll add 18 to it. It would become 46. So 46 is somewhere over here. We'll draw a line over here and then we'll get down and we'll see that it is around 65 hours would be the time taken, would be the first half-life of deuterium-90 from the graph. And this is, see, this was our original value, then we subtracted 18 from it to correct it, and then we halved it to get 28, and then we added that 18 back to get 46. And then finally we drew a line like this, and then we went down to check for the time that it would take to be for the first half-life to occur. That's all you need to know in section number 5. I hope you have understood everything. If you have any problems, feel free to write them in the comments. If you like this lecture, please share it with your friends. I'll see you guys in the next lecture. Till then, take care. Allah Hafiz.